we are in the part 2 of the first order logic lecture. So here in the last lecture or last video, we have talked about the quantifiers and the other constructs, of course. But as we have mentioned in the last lecture or last video, that these quantifiers are very important in first order logic. Let us see other related constructs relevant to these quantifiers, right? So we can do nesting between the quantifiers. So that is required when we try to model different kind of other sentences. So let us take some examples like brothers or siblings, right? So how do we represent that? So we know that brotherhood is a binary relationship, right? So what we can write? We can write that someone is a brother of someone else. So you say brother xy, right? Xy is a brother, right? X is a brother of y, right? And from this you can say that x is a sibling of y, right? So you can write sibling xy. So it means x is a sibling of y, and it should hold true for all x and of course for all y. So we are nesting this with this, right? So you can think of x to be instantiated with x1, x2, and so on and so forth, and y. So these are the domain of x, and this is the domain of y. So the values they can take, right? y1, y2, etc., etc., right? Now we can see that for one instance of x, which is x1, you can relate to y1. You can say that y1 is a brother of x1. You can relate y2 to x1 and so on and so forth. And for x2, you can also do that, right? So you are trying, you are some way you are doing a cross product of this variable and this variable, or domain of this variable or domain of this variable. So this is called nesting, right? So we are nesting one universal quantifier inside another universal quantifier, right? Let us try to model this. A sibling is a symmetric relation, right? So how do we model that? So to model that, we'll write something like this. So sibling xy will also mean sibling yx, and also sibling yx implies sibling xy, and this should hold true for all xy. So this is also a kind of nesting. So we are just uh, writing it in a shortened way. So this actually means for all x, for all y. So we can shorten it like saying for all xy, right? Now the third thing that we like to model is everybody loves somebody. So in order to model everybody, so first let us write the predicate, that is loves, right? So loves x, y. Now we are stating this for all x. So you have to write for all x. But this x, they can love somebody. They may not love everybody. So in order to model some, we say that there exists y where uh, mm, if you have one x, that person loves one uh, at least one person. This one person can be anyone, given which person you are selecting as x, right? So it encodes that everybody loves somebody, right? Now let us move to other kind of constructs. We will be doing the reverse here. You are given with a first order logic formula. From that you have to come up with the corresponding natural language, say maybe English statement, right? So it says there exists y for all x loves xy. So this is not something similar to what we have done in the last example. So it basically says that uh, everybody, so this is where x for all x is coming, everybody, so there is someone, so this is your y, there is someone, let's say y1, right, who is loved by all. So all loves x. So how do we write, visually see it? So you have, for x you have got value like x1 x2 to xn, right? Now for y you can have y1, y2, etc, etc. So this is saying that there exists at least one, like say y1, it may be y1, it may be y2, or it may be both y1 and y2, where everybody loves x, loves y. You can think everybody who loves y. So you see that y must be very popular, right? So it says that there is somebody, there is somebody who is loved by everybody, right? What about this? So this says there exists x for all y loves xy, right? So you can tell what it should be, the corresponding English sentence. So there is somebody, so there is somebody, which is x, who loves everybody, right? So there is somebody who loves everybody, right? Now there can be a confusing case like this. So you have for all x, crown x, or there exists x, brother Richard x, right? So here we are pretending that x, this x is a crown, and here we are trying to say that x is a brother. But the point that you should note that this x is coming under a different, or coming with a different quantifier than this x. So you can treat these two x's to be different. So these two variables are different, right? So to normalize this, so you can replace this x to be z and this x to be z. Then you will not have any problem. So though it looks like to be a confusion, but as the scope of this x is this quantifier, this existential quantifier, but not this quantifier, we can rename it with a different variable, and then the confusion, no, there will be no confusion, right? Now this universal quantifier and this existential quantifier, uh, they have some beautiful relationships between themselves. So you can convert one form of quantification to the other form. So let us take some examples and try to see the relations that hold between this universal and existential quantifier. So the first example that I'll try to take is everyone dislikes YouTube ad. Now you can rephrase this in two different ways. So one is that everyone does not like YouTube ad. So how we can model that in first order logic? So for all x, because you have everyone, does not like. So first you have to write likes X, say YouTube ad, right? And as you have a does not here, we say a negation of this, right? Now, what is the other way to say the same thing? The other way to say the same thing is there does not exist someone who likes YouTube ad, right? So, first let us model there exists someone who likes YouTube ad. So, how do you write that? We write that something like this. There exists X likes X YouTube ad, right? And you have to put negation to the entire thing because this not is covering this entire statement, right? So see, you can write the same thing in this way. Now you take this likes, this predicate to be P. So this predicate is your P. So what it is coming to be? So for all X not of P, and this is coming out to be not of there exists X P, right? And we know that they are saying the same thing, so they should be equivalent, right? So we are saying that they are equivalent, right? So what is happening? We are moving this negation outward. So as we are moving the negation outward, the universal quantifier, it is getting changed to an existential quantifier like this, right? So you have an equivalence relation between this universal and existential quantifier like this. So let us take another scenario, so which says that everyone likes ice cream. Again, we have got two ways to say the same thing. The first way says that everyone likes ice cream, right? The same thing, right? So how we can write that in first order logic? Say for all X, right, likes X, say ice cream, right? Simple to write. And the second way of saying is this: there is no one who does not like ice cream, right? So first let us encode that not do not like does not like ice cream. So how do we write that? So we write that something like this: likes X ice cream, right? And we need to now say that there is no one. So this part. So how do you write that? You just simply say there exists no one, right? So again, this is your P. So this part we can say for all X P, and this part can be written as, so they are equivalent because they are saying the same thing, not of there exists X, not of P. These two are equivalent, right? Let us go to another example, which is Indian cricket team has a captain, right? So again, we have got two ways to write the same thing. There exists someone who is a captain in Indian cricket team, right? So in first order logic, we can write there exists X captains X Indian cricket team, right? Now, what is the second way? The second way is that it is not the case that there is no captain in India cricket team. So no one captains Indian cricket team. It is not that case, right? So let us first write captains Indian cricket team like we have written earlier. Captains X in C team. And how do we write there is no captain? We just say we negate, and it is true for uh, uh, it is not true for any case, right? So how do we model that? We just say negation for all x. So for no case it is going to happen, right? So now we can see that we come up with another equivalence relation, like there exists xp equivalent to negation there exists for all x negation p. So here what we are trying to do, we are moving this. If we move this inward, this negation inward, this will flip the sign. It will become there exists a, and this not and not, they will become to be true. So we have got p. So you can see that we have got this, right? Now the fourth one, or the last one, between the relation, concerning the relation between this quantifier, is some persons dislike war, right? So what is the first way we can say this thing is there exists some person who dislikes war. So how do we write that in first order logic? We say there exists someone who dislikes war. So not likes x war, right? And what is the second way to say this? Not all the persons like war, right? So let us first write all the persons like war, right? So for all x likes x war, and it is not the fact, so we just put a negation before this. So what it will come to, there exists x not of p is equivalent to not of for all x p, right? So it's like you are moving this inward. This will be flipped to there exists, and not will be coming before this p, right? So you see that this one form can be converted to other form. So there is another important thing, another important construct in first order logic, that is equality, right? Now this equality just relates two terms and declare them to be mm, they declare them to be equal, right? So you can think this to be a predicate again, right? So it is a special kind of predicate which asserts equality between two terms. So one term can be a function like this. For example, here I'm saying that father of Superman is Zor-El, right? So you are relating Zor-El, which is an object, to the value of the function father of Superman, right? But it also is useful when you try to discard some self-referential relation. Like you want to model something like this: everyone is a friend of others except himself. Now, how do you first state everyone is a friend of others? So it is very easy to write for all xy friend xy, right? And you need to assert this except himself. Now this, when this himself will come into picture, if x and y they are same, so you want to have this x and y, x equal to y, to be false, right? We are putting a negation before that. So this will, if you have something, a friendship relation between x and y, that will imply that x is not equal to y, or also vice versa, right? So if x is not equal to y, then they are friend to each other, because we are saying that everyone is a friend of others, right? Now there is another situation where we make use of this equality, is when we want to have some property to be held more than once, right? So for example, Richard has at least two brothers. So how do we write that? So first let us try to model that Richard has two brothers, right? So we can find two persons or two entities or two objects, X and Y. So the first object X, so X is a brother of Richard, and Y is also a brother of Richard. So Richard, but if you don't do anything else, it might so happen that you have chosen this X and Y to be the same person. If that is so, then it may end up with the fact that Richard might have only one brother, right? In order to prevent that, you have to add another clause like X is not equal to Y. So if that is so, you can see that Richard has at least two brothers, right? So this is another situation where you might want to use the equality symbol. Now let us take an example domain and try to model that using first order logic. So domain is the kinship domain, where you have got the family relations, the persons. We will be using the unary predicates like male, female. So that is to say that someone is a male. So these are called unary predicate because they are having only one argument. So one argument. So these are called unary. And brother, as you have seen, they are binary predicate or relations, right? So the other examples of binary relations or predicates are like parent, sibling, brother, sister, and so on and so forth. You have functions like mother. So mother of someone, mother of X, say, is equal to Y, right? So these are the kind of constructs we are going to use, right? So let us first try to model this fact that one's mother is one's female parent, right? So here we are trying to define the concept of mother, right? So how do you model that? We say that uh, there is someone like say C, right? And for C, the mother of C is M, right? When it is true, when M is a parent of C, right? M is a parent of C and this M is a female, right? M is a female, and you want it to hold true for any mother and any child, right? Now let us go to the second example, which says that one's husband is one's male spouse, right? So here we have modeled this mother to be a function. But let us try to model this husband to be a predicate. We could we could have done it with a function also, but let us do it. Assume that it is a predicate, right? So you have a husband relation or predicate, right? You have a husband relation, and you have one husband and a wife, right? So then, so the other way of this would also be true, of course, if you can think a little bit. So first of all, they are spouse of each other. So you just say spouse HW, and H is male, right? So it is this H is a husband is a male spouse, right? And it should hold true for all husband and wife, right? Now coming to the third statement, which is male and female are disjoint categories. How to model them, right? So you have, so again it should be bidirectional, because if someone H is a spouse of W and H is male, then H is a husband of W. So the other way of implication is also true, right? So now coming to this statement. So let us write male X. So if someone is male, male, then that means that person is not a female. So X is not a female, right? And of course, the other way is also true. If someone is not a male, then that someone is not a female, then that someone is a male. And this should hold true for all X, right? So how do we represent this statement that says parent and child are inverse relation, right? So you know that this is true, right? But how to model that in first order logic? So let us write the parent relationship. So parent, say X is a parent of Y, right? So that means Y is a child of X, and the other way is also true. If someone is a child of X, so Y is a child of X means that X is a parent of Y, and this should hold true for all XY, right? uh, how to define a grandparent concept, right? So a grandparent is a parent of one's parent, right? So it is a kind of uh, chain of parent relationship, right? So you have say one uh, mm, grandfather who is a parent of say one person, say X, and this person is a parent of child, then we can establish a grandparent relationship between G and C, right? So we say grandparent GC holds between G and C if we can find at least one parent, right? It can be multiple when parent when P is a parent, sorry, G is a parent of P, we are modeling this part, and P is a parent of C, right? And you can see easily that if this is holding true, the other part is also true, right? So this should hold true for G and C. Now, how do you define the sibling relation? Sibling is another child of one person, one's parents, right? So you have a parent which is P, you have say X here. Uh, mm, so this P is a parent of X, and you have another child say Y of P, and you have to make sure that this X and Y, they are not equal, right? So let us see how to model this, right? So you say sibling XY implies, first we need to make sure that X is not equal to Y, right? And we need to find an intermediate node like this, right? So who is a, so we need to find a P who is a parent of X, right? Who is a parent of P is a parent of X, and P is also a parent of Y, right? So you say parent P, Y. So this models the sibling relationship, and of course you need to say for all x, y, right? Now, when we talk about knowledge engineering in first order logic, so basically you want to encode the knowledge about a domain, right? And you want to do that to solve certain tasks, right? So that's why you need to start with thinking what could be the possible set of tasks in hand. Then uh, to relate this task you need to find the relevant piece of knowledge that relates to this task, right? And the next task is to decide on how to encode this relevant knowledge by defining a set of vocabulary. So what do we mean by identification of task? So if you think of this Yumpus world, the agent needs to choose an action, like whether to grab the goal, whether to throw an arrow, whether to move forward, whether to move up. So all those sort of things, and it is also required to get some answers relevant to the environment. For example, whether if we have whether you have a pit in a neighboring square, or if you have impulse in a neighboring square, right? Now you have to take help of the domain experts to know about the domain, to know about the relevant knowledge of the domain, right? It can be collected in an informal term, like you ask the uh, mm, domain expert to write down the piece of relevant information, right? Then you have to decide on the vocabulary. So you have to translate this informal description into a formal description. Like you have to define the concepts. You need to say what are the predicates, what are the functions, what are the constants, right? So for example, in the Yumpus world, you can model something like a square contains speed as a function. It can be a predicate, or it can be a function. So these are the kind of decisions that you have to make as a knowledge engineer. So the next thing is to make a certain generic statement about the domain. So for example, if you find a you feel a breeze in one square, you have you might be having it in the neighboring square. So these are kind of general knowledge about the domain. So these are, or you can say that what is the definition of a mothership relationship. So these are the kind of axioms which are thought to be true in the domain. Now you have to encode a very specific instance of the problem, right? And finally, you have to pose queries to get the answer. If you have certain issues, you need to debug the knowledge base, right? So to encode the general knowledge about the domain, you have to define all the axioms that concerns the different vocabulary terms. So for example, in the kinship domain, you had got the mother, then grandparent. So these are the kind of all the definitions you have thought about, and concepts you have thought about, you're defining here, right? And then you have to come up with the mm, encoding of the specific problem instance, like the agent is you have got a square grid, your one grid is a neighbor to the other grid, then the agent is sitting at the first left bottommost corner of the grid. So all these are specific problem instance, right? Now then you can ask query ask the inference procedure to come up with new facts, and as you derive new fact, you can use that new fact for your purpose, or you can come up with a fact that you want to test also, right? And finally, if you have certain problem, you need to get back and see what are happening. You need to kind of debug the knowledge base, whether you have certain inconsistencies while you have defined the knowledge base. So to illustrate all these steps, let us take an example picked up from the book of uh, artificial intelligence, a modern approach. So this example concerns an electronic circuit consisting of the XOR gates and AND gates and OR gates. So we have got three types of gates here, and this circuit has got three inputs: input 1, input 2, and input 3, and has got two outputs: input 1 and input 2, output 1 and output 2, and the name of the circuit is C1, right? And you can see by looking it is a kind of modeling an adder circuit. So it is an adder circuit, sorry. Uh, so it is an adder circuit with carry. So these are the addends A1 and A2, and this is the carry, right? So the first thing that we need to do is to identify the task. So what can be a task, like whether the circuit adds properly, right? So it is a kind of verification that we are doing over the circuit. So we have got certain input, like if we have 1 1 1, so this is your A1 and C1, whether the result that we get from the circuit or the model is actually what we get from the, so this is your actual. So if we say this is x1 and x2, whether x1 and x2 they are same, right? So this is actual, and this is the represented, the first order logic representation. You are inferring this x1, right? uh, Also, you want to know at a given situation what are the inputs and outputs of certain gates. Like at certain situation, what would be the output of, say, XOR gate 1 or XOR gate 2, right? Now the next step is to assemble relevant knowledge. So what do we know about the circuits? And of course we know that they are composed of wires and the gates, and there are different kinds of gates, like AND gate, OR gate, XOR gate, or NOT gate. Of course, needless to say that for this task, the physical parts or the size, shape, color, etc., they really do not matter. So they are irrelevant. We don't need to model them, right? Then we need to decide on our vocabulary, right? So the vocabularies, we need to define the symbols, the predicate, the functions, and other things. So we need to think whether we can model the gates as different objects, whether the type of the gates, they can be determined by their behavior. So there are different alternate representation of the same thing, that that x1 is a type XOR, right? So we can model it as a function, we can model it as a predicate, or we can just use XOR as the predicate name instead of type as the predicate name. We can follow any one of them, right? So how do we model that a signal is off or on? So we can have a predicate, say, on, or a function, a signal t1, which might be assigned a value 0 or 1. If it is 0, then we assume it to be off, the terminal is off, or if it is 1, we can assume that the terminal is on, right? How do we represent the connections, right? So what is the input? So this into x1 is a kind of function that tells you, or that refers to the second input terminal of x1, right? Likewise, this out1 x2 refers to the first output terminal of the gate x2, right? And we can say that two terminals T1 and T2 are connected. So there are different possibilities. We can take any kind of design, and then we have to be consistent on using those decisions that we have made. The next step is to encode the general knowledge of the domain. So what are the general knowledge? the first general knowledge is, or the axiom is, so these are all axioms. So the first axiom is, if two terminals are connected, then they have same signal, right? So first let us write what do you mean by connected. How do you model connected? So connected T1, T2, right? So they are connected means they will be having the same signal, right? As they are connected. So signal at T1 should be equal to signal at T2, and this should happen for all T1, T2, right? Now let us model the next statement. Sorry. The signal at every terminal is either 0 or 1 but not both. It is also known to be true, right? So we can say that if the signal at T is equal to 1. So if we say this signal at T is equal to 1, then what it should imply? It should imply that it is not the case that signal at T equal to 0, right? And the other direction of the implication is also true. If the signal at a terminal T is not 0, then that signal at the terminal should be 1, right? So we can make it to be true for all terminals. But we are not done yet, because this 1 and 0, they are mere symbols, right? They might be said to be equal. So in order to prevent that, we need to explicitly say that 1 is equal to 0. 1 is not equal to 0. So this is the second thing we have to assert to ensure this, right? How do we model that this connectedness is a commutative predicate? So we can simply say connected T1, T2 implies connected T2, T1 or vice versa, and this should hold true for all T1, T2, right? Now we need to define an OR gate, right? And for OR gate, what we know to be true is that uh, uh, an OR gate's output is 1 if and only if any of its input is 1. So let us see how to model this, right? So we say that the type of a gate is equal to OR. So that implies the other thing. The output is 1 if and only. So this if and only, whenever this is present, explicitly you have to model that with both way implication, right? So how do we model that the output is 1? So we model that with something like this. Signal at the out terminal, or the first terminal at the output of the gate T, is equal to 1. Signal is a function, right? So this will imply, and of course both way imply, because we are modeling if and only if there exists one input terminal where the signal is 1, right? So in G uh, should be equal to 1, right? So this is how we define OR gate. So similarly, you can define AND gate, which says an AND gate's output is 0 if and only if any of its input is 0. So how do we write this? We can write this in a similar way. So we need to say for all G, for all G. So for all G, type G equal to AND implies a signal at the output. It has got only one output terminal, which is 1. G equal to 1 if and only if you have at least one terminal, right, where the signal is 0. So I think I have made a mistake. Here it will be 0. It will be 0. So signal, there it is at least one terminal where the signal is input terminal where the signal is 0, right? So we just say in ng equal to 0, right? This is how we define AND. Now how do we assert some properties of XOR gate? So an XOR gate's output is 1 if and only if its inputs are different. We have to do it differently. So we know that it has got two inputs. If the inputs are different, then we can say that there the output of OR gate is XOR gate is 1. So for all G, it will be kind of similar, but there will be some changes. G equal to XOR, right? That means signal out 1G equal to 1 if and only if signal, it has got two input terminals, right? So signal in 1G, it is not equal to signal in the second input terminal, right? So this is how we can define the property of the XOR gate, right? So how do we define a NAND gate? Very simple to do. Basically, the input and the output terminals, they have different signals. So signal values. So I can write for all G, type of G is not, right? So this implies what? That signal in the input terminal, it has got only one input terminal. It should not be equal to signal in the output terminal. It has got only one output terminal. So this is what we can write for NOT gate. We know for NOT gate, right? Now we are done with the formal modeling part. Let us encode a problem instance. So this is our problem instance. This is what we know. So we know that x1 is, so whatever we discussed earlier, they are very generic statement about AND gate, OR gate, and they can be applied to any circuit. But here we are talking specifically about an adder circuit which adds with carry, right? So the type of x1 is XOR. So this is what we are mentioning. Type of A1 is AND, and we are also asserting the type of the others. We are explicitly mentioning the connections, like the output of the first terminal of the first XOR gate, that is this one, is connected to the input of the first terminal of the second gate. So basically this terminal, right? So we are saying that so you can pick up one randomly. For example, connected out one A2. So the output signal of output terminal of A2 is connected to the input terminal, first input terminal of O1, basically this, right? So you can see that we are writing the predicates to encode this problem instance, and we can do for the others which have not been mentioned here, right? So the next task is to pose queries to the inference procedure. So the first query that I like to put is what combination of inputs would cause the sum bit to be 0 and the carry bit to be 1. So how we can encode this query? So we want to have the values of the signals, right, at the two adder inputs, addend inputs and the carry input. So we need to think about the three variables, right? So we have three variables, I1, I2 and I3, right? So the signal at input terminal of the first input terminal of C1 with the circuit is equal to I1, and the signal of the second input terminal of C1, which is your circuit, is I2, and the signal at the third input terminal C1 is equal to I3, right? And we need to have the sum bit to be 0 and carry bit to be 1. What is the sum bit? Sum bit basically is the first output terminal of C1. So signal out the first output terminal of C1, what this should be? This should be 0, right? And signal out, say, to C1, there is the second output terminal of C1, it should be 1. So this is the sum bit. So this is the sum bit. So this is the sum bit and this is the carry bit. So if we pose this query, so these are the kind of results we can get, that I1 can be 1, I2 can be 1 and I3 can be 0. I1 can be 1, I2 can be 0, I3 can be 1. I1 can be 0, I2 can be 1 and I3 can be 1. So this is the answer to my query. So this is the answer we receive in response to this query, right? Now similarly, we can also model this query like what are the possible set of values of all the terminals for the adder circuit. So I'll leave it as an assignment for you to do, right? We will not be talking about the inference algorithms of first order logic. So though you'll be talking about the inference algorithms for the logic family to realize semantic web, inference in semantic web, but there are certain important facts to be known about the inference in first order logic knowledge base. So let us see what are the kind of inferences. They're concerning the inference algorithm. So in 1930, Kurt Gödel, the famous mathematician, who basically conjectured that there is a complete inference procedure for first order logic, but he did not demonstrate the algorithm, right? So this is the kind of thing that I'm trying to stress, is that complete inference algorithm. So if the And if you can remember what is completeness, that if a particular fact is entailed by the knowledge base, that is also inferred by the inference algorithm. So for first order logic, Gödel conjectured that there is, one can find one inference technique or algorithm that is complete, right? Now, back in 1965, Robinson, he provided something called resolution inference procedure, right? So I'll not be talking about the inference algorithms. If you are interested, you can go to the chapter 9 of the AI in Modern Approach book. But this is an important result, right? So this resolution inference procedure, it is both sound and complete. And you know that this is the kind of uh, mm, inference algorithm that we always want to have, right? But there is an issue with first order logic. So the issue is that the inference is first order logic is semi-decidable. So what do we mean by semi-decidable? So the first characteristics of any semi-decidable logic family is that this the reasoning terminates with a proof or explanation if the conclusion is entailed by the knowledge base. So this is very important. So you know that a conclusion is entailed by the knowledge base. So if this is so, then the reasoning process will terminate within a finite amount of time with an answer. But if it is not entailed, if the conclusion is not entailed, then your program might never halt, which is a kind of um, mm, not a good thing for semantic web, right? So for semantic web, you need to have an inference algorithm which is decidable, which is decidable. So this is what you want to have. You want your agent to come up with an answer within a finite amount of time, and if it cannot give you an answer, it will say that I cannot find an answer, right? So you need to find it within a finite amount of time. So we need to check what is the kind of logic family we can use for reasoning in semantic web which is decidable, right? So let us with this, let us stop here and park the discussion on reasoning and logic at this moment. In the next lecture, we'll start talking about the backbone of semantic web, which is basically the resource description framework. Thank you very much.